Welcome everyone to the Seawater lecture. Just give me a second here to share my screen. So you want to remember that this PowerPoint lecture by me is using the mini PowerPoint, the one found in your weekly folder. You're going to notice that this very first slide here, this chemistry-based slide, it's a water molecule. That is one of about 12 slides if you use the larger, more comprehensive PowerPoint found under the Content tab. Remember, each week there's always a larger PowerPoint that has all of the notes embedded, and then a mini PowerPoint, which is what we're looking at here, that will be found in the weekly folder. The mini PowerPoint has the voiceover by me, which is what I'm doing now. The main PowerPoint has the notes rather than the voiceover. I just want to point that out because this particular PowerPoint starts with chemistry, a lot of chemistry. If you're unfamiliar with chemistry, not comfortable with chemistry, haven't done chemistry in a while, and you don't usually go back to those other PowerPoints, you want to make sure this week that you do so that you're familiar essentially with chemistry in its basic sense. So we're looking at a water molecule. Okay, so everyone's familiar with the periodic table of elements. Elements are individual, right? So we have the element of hydrogen, that's represented here by the H, and the element of oxygen, represented here by the O. They are covalently bonded to each other, and they then make a molecule, okay? Again, that's basic chemistry, okay? What we're going to start with, of course, is that joined, bonded molecule, water. Now we're doing oceanography, so of course we're going to have water with salt in it, but before we can put the salt in our water, we need to understand water and its amazing properties. So of course we have 2 hydrogen and 1 oxygen. That's the first thing you should notice. Notice that the hydrogen are smaller than the oxygen. Notice that there are 2 hydrogen and 1 oxygen, so we have an unequal number. And you'll notice what I call, in this case upside down, but upside down Mickey Mouse ears, right? Or you can call it Princess Leia's buns, right, on her hair when she has the little buns on the top, again, upside down in this particular figure. But what you can see is that it's a kinked bond. In other words, the hydrogens are not straight across in a horizontal line, right? You don't have yellow, blue, yellow. The yellow is sort of kinked. You have this angle, right? Literally almost a 90-degree angle. So what that means is that this water molecule, again, between hydrogen and oxygen, covalently bonded, it's polar. Polar means it has an uneven distribution of electrical charge. You'll see the electrical charges shown here. So you have a minus electrical charge or negative electrical charge on the oxygen and positives on the hydrogen. So if you have an uneven distribution of electrical charge, which is again based on the positive and the negative, plus the hydrogen being smaller than the oxygen, plus the fact that there's 2 hydrogen and 1 oxygen, covalently bonded, it allows for that to have really unique properties that the polarity sort of represents. Okay, so the very probably 5 or 6 next slides are going to show you what that polarity means and what makes water so special because of it. The only other thing I want you to notice on this particular slide is the hydrogen bond. Okay, so one water molecule right here can bond with another water molecule via a hydrogen bond. So you have a covalent bond between hydrogen and oxygen within the molecule itself, and then a different bond, a hydrogen bond, that bonds hydrogen to the next oxygen in the next corresponding water molecule. Okay, so that polarity word, okay, there it is, polar. Polarity is just sort of the plural for it. It tells us that that makes it really unique because one, it will attract other water molecules, again, via that hydrogen bond. And that attraction allows the charges of the positive and the negative to link together. So it allows water to have really cool, unique capabilities, like walking on water, right? Cohesion is essentially the fact that even though water in its liquid form seems weak, right? It seems you could jump in it and it makes ripples, it makes waves, the wind can blow and it will move in the direction to which it's pushed. It's actually really, really, really strong. And that bond, that hydrogen bond, and then the covalent bond between the hydrogen and oxygen within the actual molecule itself, actually give it this ability to hold tightly. What it also does, though, most importantly for purposes of this course, is it allows it to then break and make the bonds and therefore change states of water. So if you add heat or take away heat, that water molecule, the bond between them, will break, okay, forming a different state. So let's think of liquid first, okay? Think ocean water, liquid, it's moving, okay? What happens in really warm tropical areas over the equatorial region? Well, some of that surface layer of the ocean can essentially off gas and become a gaseous form, liquid to gas. Think of heating a pot of boiling water on your stove. You put liquid water in, you turn the heat on, heat sources at the bottom. All of a sudden, you see bubbles, right? You see steam coming off the top. Then you put the vent hood on so that you don't ruin your cabinets, right? So that's a liquid to a gas. I could also take that same liquid and move to a polar area, a cold area, or for purposes of this lecture, put water in an ice cube tray and put it in the freezer, and you'll get ice cubes. You'll get solid. So water can change state from solid to liquid to gas and back again over and over again. In other words, I could melt those ice cubes after I take them out of the freezer. Okay, that liquid can then become solid again. Solid can become liquid. Liquid can become gas. Gas can become liquid over and over and over again. That's the hydrogen cycle. Okay, the water cycle is in our systems. So this figure is meant to represent that for you. And what it's telling you is that heat, okay, essentially 100 kilocalories. Heat can either break the bonds, causing it to warm, going from a liquid to a gas, or you can take away heat, the same amount, 100 kilocalories, and actually cause it to become a solid. Notice that these arrows make a complete circle. In other words, this is a circular path. Once it freezes, it doesn't stay frozen. Once it evaporates into gas, it doesn't stay gaseous. Depending on whatever temperature it is, when you add and take away heat, it can change state. From an oceanography perspective, that's really important because what that does, of course, is it lets us know that we can have different temperatures of water on our planet, both in the air and in the ocean, of course, and that different densities of those temperatures can actually impact the mobility and the form or phase that that water is in. So we all know that ice floats in the ocean, right? Now, that should seem pretty obvious, right? But you want to realize that what's actually happening is that the ice is the freshwater portion of the water in the ocean, the least dense portion that freezes quicker and stays on the surface because it's less dense. And then the salt water, the saline water, the more dense water, is what's underneath it. If you think back to lab one, why does a metal boat float? Because the metal boat is less dense than the water that it's in. Well, why does ice float in the ocean? Because it's less dense. The fresh water that makes up the ice is less dense than the salt water that's supporting it. Now, that's not 100%. In other words, the ice doesn't sit on top of the water, it floats in the water. Okay. And for those of you questioning, what do you mean there's fresh water in the ocean? Remember, the ocean has a salinity, but that salinity is not 100%, right? So when it rains, when you have upland runoff, when you have any freshwater source, a river source, for example, that is inputting fresh water into the salt water. That fresh water then, of course, is less dense than the salt water that it mixes with. Again, think back to lab one. So as this slide is pointing out to you, the density of water will increase as water is cooled. Okay, so as you make water colder, the density increases until it changes state to a frozen state or solid state. And then, because it essentially expands, right, the amount of space it takes up increases, its volume increases. Therefore, the ice then becomes less dense than the water. So if you have really cold water, for example, at the bottom of the ocean, that's more dense than warm water at the top. But remember, those are both liquid. If you have really cold water, so cold that it goes from liquid to solid, its density will change because its state has changed. So ice is the least dense in that case. Okay, so here's what I was talking about with the ice cubes. In other words, if you were flying overhead in an airplane or driving by on a boat, all you'd see is this portion. But really, this is frozen fresh water. So it has some density, of course, right? If this gets bigger and bigger and bigger, eventually it can become lower and lower and lower, like isostatic equilibrium when we talked about the convection current and essentially the movement of the asthenosphere with plate tectonics. Same concept. What we're highlighting here, though, specifically is density, okay? And that density changes as state changes. You're going to be asked on page 61 of your lab book to actually use a density curve. What this is going to do is it's going to let you be able to essentially combine the two principles of water in the lab to come up with the concept of how density is interrelated. In this particular figure, it just has temperature on the x-axis and density on the y. On page 61 in your lab book, you're going to have salinity on the x-axis and temperature on the y-axis with density as a result, and you'll get these density curves. So here's a good way of you understanding where those density curves come from. This particular density is showing you exactly like you did in lab number 1, right? This is a number less than 1, so this clearly must be fresh water, right? So what they're doing is they're figuring out the density, and as it freezes, so as the temperature decreases, the density decreases as well. You're going to notice that in particular in a liquid form, as temperature decreases, density increases until, see there it is, increasing until you change state. That's the first portion and most important part that you want to take away from the concept of the water molecule. Okay, it is polar. Therefore, it can have very unique properties of cohesion, and most importantly, it can exist in 3 states, and those 3 states, based on adding and taking away heat, can change all over the planet. Next important component about water, again, we're still talking about water and not necessarily salt water yet, is that it's considered what's called a universal solvent. Okay, just like in the blood groups, type O is a universal donor. Anybody can get it, right, as a blood transfusion. Well, water will essentially dissolve anything into it. In other words, if you have water and you put food coloring in, the water takes that food coloring and takes bright red and makes it slightly less red. Okay? Or if you had water and soda and you added the soda, it would dilute the soda, it breaks it down. So it will solve, right? It will dissolve anything you put in it. When you mix water with something else, it's called a solution. Okay. In that solution, the solvent is always the water, and the solute is what you put in it. Okay. So the solute in my examples were the soda and the food coloring. In purposes of seawater, it's going to be the salt, right? When we put salt in water, salt is the solute and water, H2O, is the solvent. Now here's where some numbers are going to get thrown your way. Do not get scared by these numbers, okay? Don't get overwhelmed by the numbers. Just make sure you're paying attention to the differences between the numbers, okay? So I'm going to show you a pie chart. And that pie chart, think of like Trivial Pursuit, right? It's a circle, okay? So it's an equivalent of 100%. And what you're going to see is that 96.5%, the vast majority of it, is hydrogen and oxygen, H2O. The remaining 3.5% is the stuff, solutes, that would be dissolved into it. Those solutes, most predominantly, are sodium and chloride, which is what makes it seawater or salt water. But they're not exclusively just sodium and chloride. All of the solutes are 3.5%. These solutes, when added to the water, very important, change the property of the water. If they change the property of the water, they can change the freezing point, the boiling point, the density, etc. So here's that pie chart I was talking about. Okay, so here 96.5% hydrogen and oxygen, okay, the universal solvent, and the solute, the other components, are 3.5%. Now here's your first chance of seeing the word salinity and noticing now where the 34.5 or 35.5, depending on essentially who you ask or where you are in the world, open ocean salinity. Okay, so we usually say 34, 35, 35.5, open ocean. So that salinity would be 3.5%, right? Because we're using grams. Okay, so this amount, 34 out of 1,000, would be 3.5%. Of this part of the pie chart of just the orange, that 3.5% is then broken up predominantly into sodium and chloride. Here they are, sodium and chloride. That sodium and chloride make up 85% of this pie chart, and the remaining stuff, the extra stuff, can change essentially where you are in the ocean. If you're at the bottom of the ocean by a hydrothermal vent, or by a mid-ocean ridge system, or an area where you have an oil spill at the surface, or even an oil leak at the bottom, right? Anywhere that material is added or taken away from the ocean, it can change what the other components are. So much so that we even have a category, this purple one, called other, right, to account for it. These others are the basic components of what you typically would find, again, in the whole surface of the ocean, not necessarily just at the bottom, not necessarily just by the coast. Okay, so I don't want you to focus on what all of these are or the percentages for that matter. The most important part is that sodium and chloride are the most comprehensive, the largest, right, the most in amount of the total solutes right here in the water. And that is why we say it's saline, salty. Okay? The salinity is the percent of those dissolved amounts of sodium and chloride in that water body. Okay, so putting that together now, we have our seawater, which is salt water, with 96.5% water, 3.5% stuff, okay, or solutes that are dissolved. Of the 3.5% stuff, we said that sodium and chloride were the two most predominant. If you look back at that pie chart we just had, they make up 85% of that total little small piece. That other category, which included other and the other stuff like bicarbonate, etc., that makes up 15%. Again, you have another 100% here in math. Do not get confused by this percentage up here. They're two separate numbers, okay? When we look at the 3.5% and dive in, that's where the 85% applies. So of the 3.5%, 85% of all of those solutes are sodium and chloride. So now that we've spent so much time talking about salt, we should actually understand how water and salt are related. Okay, so we already know about our Princess Leia or Mickey Mouse ears. Here's our hydrogen covalently bonded to our oxygen. This water molecule can bond via a hydrogen bond to this water molecule. But if other stuff gets introduced into the water, since water right here is a universal solvent, it will dissolve whatever you put in it. So if you take basic table salt, which has sodium and chloride, this is essentially saying that's what's dropping into the water, it will then show up as sodium, Na, and chloride, Cl. Again, more elements from the periodic table. And what water will do is surround each of these molecules. Here it is surrounding a chloride. Here it is surrounding a sodium. It will surround each individual molecule and dissolve it or break it apart. All of this will get broken apart. Hydrogen and oxygen will surround each, or water molecules will surround each, and it will break it apart and it will give you a solution of salt water, sodium and chloride, salt in the water, H2O. We then call that seawater. Remember, 3.5%, right, is sodium and chloride. Of that, 85% then gets broken down, giving us our total salinity. Okay, so here's your textbook definition of salinity, total concentration of all dissolved inorganic solids. 35 ppt, roughly 35.5, depending on where you are in the open ocean, is about basic open ocean salinity when you take everything from polar regions to temperate regions to tropical regions from the surface to the deep. There it is, 3.5%. Okay, so now you see where the translation is. We then write it as 35 ppt, parts per thousand, or sometimes they get fancy and put these little zeros, which means essentially the same thing. Okay, it's like shorthand for science. Remember, I told you that in general, the average is about 35, 35.5 parts per thousand. And that's because you'll notice that we don't just have a salinity curve that stays even as a straight line. Okay, it's really low in some areas, and by really low, it's still over 34 ppt. Okay, so remember, 0 would be low. That'd be nothing. That'd be fresh water. Okay, so open ocean salinity goes from a low of about 34.2 at the South Pole to a little higher. Okay, 34.56, 557 or so at the North Pole. That increases dramatically at the temperate regions, then decreases again in the equatorial regions, but it doesn't decrease to the level that the poles have it. What this shows us, all that is important to you, okay, is not memorizing what is the salinity at each location. It's that salinity is different across the entire ocean. It is different based on depth. It is different based on surface layer, based on temperature, because the temperature and the actual currents, which you'll learn about in a couple weeks, move the water around, causing the salinity to change. So when you take a general average, you get about 35.5 parts per thousand as general ocean salinity. If some of you are wondering where that sodium and chloride and the other stuff comes from, you've already learned most of it, right? We know all about erosion. We know all about how submarine canyons form, right? Turbidity currents that are coming off the surface, erosion that's coming from the upland down into the open ocean. And we also know about hydrothermal vents and mid-ocean ridges. So if we were to take a look at the general ocean, taking out our plate tectonic idea, but keeping the same concepts, we know that we have seafloor areas where material is being added through the asthenosphere. Okay, so solutes can come from those locations. We also have upland runoff, river discharge, or even just literally runoff from the mountains. That can give us material. Here it is. And then acid rain and other changes in state as we go from a gaseous form back to a liquid form, that can actually bring materials with it as well. So collectively, all of this is where our sodium and chloride come from, as well as the other stuff. Remember, there was 15% other. Okay, so that's your general introduction to salt water. Okay, giving you an intro to water first and then salt water next. This figure is the single most important figure of this entire PowerPoint. This is the one you're going to spend the vast majority of your time. This is the one that Lab 5 focuses on. This is the one that you'll be graphing in Lab 5, okay? So this is where your efforts will be. Because of that, I'm probably going to stay on this figure for about 5 minutes in this lecture so that you can really, really understand what it is I'm showing you, okay? First thing you're going to notice is that you have 3 layers in the ocean: a surface, a middle, called a peak line, and a deep. Notice that they are not equal. 2%, 18%, 80% of the total amount of the space, essentially, or makeup of all of the ocean waters. So the deep zone, by and large, covers the vast majority of the planet. It, of course, covers the ocean floor, but you'll notice that it also covers the surface layer of the ocean in polar and subpolar regions. You'll notice that the surface layer is the smallest. Okay, it's only on the surface, and it only goes from temperate regions to tropical regions. Okay, again, notice that you have your latitudes here. Okay, so first thing you want to notice is that we have 3 layers. They're not equal in size, and they're not equal in location. Let's focus specifically on this here next, thermocline. Okay, so in my introduction to this PowerPoint, I introduced you to the concept of temperature, giving density. Then we talked about adding salt, which is salinity, and that gives density. So we now know that temperature and salinity both have impacts on density, okay? And you're going to find that out also from doing the lab. So temperature, thermometer, thermo, this should then make it pretty obvious to you that this is the temperature-based change layer of the ocean. Thermocline means temperature change layer. You're noticing here that temperature is increasing on my x-axis. What is it showing you, though, about what's happening in the ocean? Well, it's telling us that temperature is highest at the surface, lowest, coldest at the bottom, and then you have this change layer right here. Okay, that layer looks essentially like that. Change, right? This is pretty uniform in the surface, pretty uniform in the bottom, you know, a couple degrees difference. But look at this huge change amount. It's telling us essentially that in that change layer, temperature is dramatically decreasing as you go down in the ocean layers. Okay, so there's your temperature explanation. Now let's look at the bottom here. We have another name, halocline. Halocline is a fancy word for salinity or salt. So we had a temperature change layer, thermocline. This is a salinity change layer, halocline. Okay, you're going to notice again that the curve up here looks like that. The curve down here looks like that, mirror images of each other. But what it's showing you regardless is that you have a pretty uniform salinity in the surface, a pretty uniform salinity in the bottom, and there's your change layer. There's the change layer. The change is happening in the middle, in the halocline. That is the single most important thing for you to notice about this particular figure, okay? What I want you to realize is if we have a thermocline, it's the middle layer. If we have a halocline, it's the middle layer. Surface layer is always called the surface and stays the same. Deep layer always called the deep and stays the same. Again, up here, surface is the same, deep is the same. Thermocline is the middle layer. Halocline is the middle layer. The thermocline and the halocline only apply to the middle layer of the ocean. Now, hopefully, you're starting to see my point. Go all the way up to here. What do we notice about the middle layer? The middle layer had a really unique name, pycnocline, right? Notice that you see the pycnocline twice here. Pycnocline is fancy name for density, density change layer. So what this is telling us is that we have the surface layer of the ocean, okay, the least dense. The bottom layer of the ocean, the most dense. Whether you talk about salinity or temperature, doesn't matter, right? Surface layer least dense and the smallest amount. Deepest layer most dense and largest amount. But the middle layer, the second layer, the single most important layer for this lecture and what you're studying in lab this week, that layer is the middle layer. It's called a pycnocline. It means density change layer. What is that density based upon? The thermocline, or temperature, and the halocline, or salinity. Now let me just take a little break here and remind you guys of one thing that in my 18 years of teaching happens every single semester. It'll happen again this semester, even though I'm telling you so now. So I want to remind you one more time. Yes, we have 3 layers of the ocean. Yes, I've introduced you to 3 new terms, thermocline, halocline, pycnocline. But this is the most important part. No, they are not named the 3 layers of the ocean. Only the middle layer has 3 different names depending on what we're talking about. So if I ask you to describe the ocean layers for me based on density, you will use this figure and you will say surface, pycnocline, and deep. Why did you say that? Because I asked you about density, and pycnocline means density change layer. If I ask you to describe for me the 3 layers of the ocean on temperature, you would use this figure and you would say surface, thermocline, deep. Why? Because I asked you about temperature. Thermocline represents temperature. If I ask you to tell me about the 3 layers of the ocean based on salinity, you will use this figure. You will then say surface, halocline, deep. Why? Because I asked you about salinity. Halocline is the salinity change layer. Okay, so again, definition, pycnocline, density change layer. Thermocline, definition, temperature change layer. Halocline, definition, salinity change layer. Where are they in the ocean? The middle layer. All of them? Yes. Okay, so don't say, oh, there's a 3-layered ocean and there's 3 names. They're named pycnocline, thermocline, halocline. That is incorrect. Yes, there's a 3-layered ocean. They are named surface. Pycnocline, thermocline, halocline is the middle layer names, depending on what specifically I'm asking you, and deep. That is why, hopefully now you understand that the pycnocline is represented as a sidebar to both the thermocline and the halocline. In other words, if you change temperature, you change density. If you change salinity, you change density. If we look at the sea surface temperatures, okay, here's where temperature comes in. It will hopefully remind you that the ocean, of course, has different temperatures all across the surface of the ocean. In polar regions, it's cold. In tropical regions, it's warm. And in temperate regions, you kind of have a mix of warm and cold, and therefore we also have 4 seasons, which will be a question that you also see this week on the lab. So if we have different temperatures being inputted into the ocean water, that allows our thermocline to develop in our middle layer. The cold, salty water will sink down. As a side view, okay, hopefully you now understand that we have a surface layer, 2% of the ocean, only on tropical, subtropical, leading into temperate areas of the planet. We have our middle layer, our pycnocline layer, which includes the thermocline and halocline. That layer represents 18% of the ocean and extends a little bit further into the northern and southern latitudes, covering all of the temperate regions. And then the deep layer of the ocean, 80% of the ocean, covers the surface layer at polar and subpolar areas and all of the deep ocean. So one more time just to highlight, okay, this is really important because it's what you're going to spend all of your time doing on Lab 5. If I were to ask you specifically about the temperature change in the ocean, you would tell me, no matter where you are on the planet, that the surface layer is the warmest, the bottom layer is the coldest. The middle layer is the change or cline change layer. It's where you have a dramatic change. Temperature drops with depth. In other words, temperature decreases as you go down in the ocean. Okay? Again, warm at the top, cold at the bottom. Change, that's the symbol for change, delta, happens in the middle. But temperature is dropping rapidly with depth. So that is what your graph looks like. Conversely, if I were to ask you about salinity, you're going to tell me that the surface layer is the least saline. The deep layer has the highest saline. And the middle, there's our cline, there's our change, drops rapidly with depth. Okay? Now, by dropping, what it's telling us is that the salinity amount is increasing. Okay? So this is going to go in the opposite direction. It's going to tell us that salinity increases as you go down in depth because you have a higher salinity. So you're increasing to this high salinity. Temperature is decreasing, right? Not in percent, it's decreasing in temperature. So there would be your halocline example. Put those two together, temperature or thermocline plus salinity or halocline equals pycnocline. Why? Because it means density change layer. Temperature has a density, salinity has a density. It's now telling us based on density that the surface layer of the ocean is the least dense. The bottom layer of the ocean is relatively constant though as the most dense. And the middle layer, still a cline, gives us change. But again, it's telling you that density is changing rapidly with depth. What that's doing, look, we're going up in number. So our density increases as we go down in the ocean. One more view, letting us remind us essentially of how our oceans are situated. Our surface layer, sunlight, happy, warm, gets hit by the sun, even in the poles, right? It's still warmer than the deep layer. So of course, we're going to have our least density. Why? High temperature and low salt or low salinity. Our bottom is going to have our highest density. Okay, why? It's going to have low temperature and high salt. The change layer, the cline layer, is literally sandwiched in between, giving us a change. What is happening there? It means that the density is changing because the temperature is changing from high to low, and the salinity is changing. Opposite, right? From low to high. You're going to hear me refer to this in multiple lectures, and you'll sort of hear that it's a good way to study that. I call this the peanut butter and jelly sandwich because students have a really hard time comprehending that the middle layer has the three names and has the three changes. Surface layer is the same, bottom layer is the same, right, in terms of their names. So if you think of a peanut butter and jelly sandwich or ham and cheese sandwich, whatever you want to pick that has two things in the middle, surface layer is a piece of bread. Deep layer, piece of bread. The change layer in the middle, the cline, what is it made up of? Two things, either temperature or salt, peanut butter and jelly, ham and cheese. You never put the ham and cheese on the top and bottom, right? They always stay in between the bread. So where does the picnic line layer stay? In between the bread, in between the surface and the deep layer. So I hope something funny like that will at least help you to remember. Okay, so now we have finished our mini PowerPoint. Don't forget to go back and look at the larger content PowerPoint if you're having any issues whatsoever with the chemistry parts.